let's look at the next rule, the best fit rule. The best fit rule, with respect to the first fit rule, has the same idea of analyzing the open bins. But differently from the first fit rule, the first fit actually look at the open bins and takes the first where the item fit. The idea is, oh, maybe, however, I could, for example, um, try to fill up and to choose among all the bins that are available and that are open, to try to put the item in that bins where the residual capacity um, is the smallest, so that I fill that up. I want to pack them and I want to make sure that I can fill bins up. So this is the idea of the best fit. While the first fit takes the first bin that is available, the best fit scans all the possible bins, check what is the bins with the least capacity, and if it fits over there. And so it puts the item over there. The worst fit does the opposite. So instead of instead of placing the item in the bin that leaves the least remaining space, place the item in the bin which has a lot of space still. So it's just a different rule, which is better. We don't know, because these are heuristic rule, but we're going to see this best fit now. Again, we have always the starting, and we still have our b equal to 0 and our for loop where we are scanning the item. Again, place is the same, has the same role. Now, however, what we need to do is to check what is the open bin with the best residual capacity, where best residual capacity is the smallest. So we have an internal loop which goes over the bins. So in this case, we have bins. So this for loop goes over all the open bins. And what it does, it doesn't store the item here as soon as it finds capacity, but it wants to check among all the items, among all the bins, which have residual capacity, which is enough to have the item. Let's check what is the one with the least residual capacity. So we are analyzing an item whose weight is weight Wi, and we check for each t whether it fits that bin t. If can fit bin t, then what we say, we compute what will be the residual capacity of this bin if we place the item I in there. And we check whether it's lower than the current best RAM, which is the current minimum value that we are considering. So this loop, basically, what it does is scan all the open bins. Among all the open bins, considers only the ones where the item can fit, and among this one, it returns that index where corresponding to the bin with the smallest residual capacity. So when we exit from this for loop, what we know is whether whether there are bins which can host which have enough capacity, and among them we know which one has the least capacity. So this is what we know from here. If there is no open bin which can which has enough space for the current item, then we will never enter this statement, and so we will never update the value of t star. So when we exit this for loop, we have two cases. Either t star is equal to -1, or t star is equal to one value between 1 and the number of bins open. So we need to evaluate this case. If t star is equal to is different from -1, it means that it's a value we have found a bin where to put the item, and then we put the bin in that item, and we update the capacity of that bin. Otherwise, if T star is -1, means that there is no open bin that could host and could have the item inside, because there is no residual capacity. So we need to open a new bin, and this is the case. So let's see this in action on the same example that we had before. I will go a little bit faster now because we understood how this works. So we examine the first item. For the first item, we need to open a bin. So the bin number 1, the first item is item number 2, whose weight is equal to 8. So the open bin now is number 1. We locate the item in that bin, and the residual capacity is 2. Let's go to the second item, which is item number 5, whose weight is 4. It doesn't fit the open item, and there is only that item, so we need to open a new bin. Now the residual capacity of the new bin is 6. So now we have two bins which are open, one with residual capacity 2 and another one with residual capacity 6. Let's see what happened with the third one. The third item, which is item number 3, has capacity equal to 7. It doesn't fit any of the two, so we need to open a new bin, bin 3, and we need to place the item in that bin. Now we have 3 open bins with residual capacity 2, 6, and 3. Let's see where we put the next item, which is the fourth item, which is item number 6 with weight 2. Now this can fit all the possible bins. All the possible bins. It can fit bin number 2, bin number 6, and bin number 3. Among all of these, we choose the one with the smallest residual capacity. So we fill this up. This is actually happens to be the same and correspond to the first fit rule, but this is just a case because of the permutation and the specific characteristic of this instance. So we choose bin 1, and so now the residual capacity is equal. So we put item number 6 in bin 1. What is it? Bin number 1 over here, and this is the loop for which checks for the minimum. And now we have located 4 items. Let's see, and we have what are the residual capacity. Now we have 3 bins open, 1, 2, and 3. Residual capacity of bin 1 is 0, residual capacity of bin 2 is 6, and residual capacity of bin 3 is 3. Let's see the fifth item. The fifth item has weight equal to 6, so it doesn't fit on bin 1. It could fit in bin 2, and it doesn't fit in bin 3, so we put the item in bin 2. Finally, and the residual capacity of bin 2 is 0. So now we have only one item left, and one bin open, and so we need to one bin open which doesn't have enough capacity for a weight of 9, because it has only a residual capacity of 3, and so we have open a new bin, which is bin 4. So again, we have used 4 bins, and we have this assignment. It happens to be, I believe, the same assignment of the first fit, but it's just a case. Now, the difference between the best fit and the worst fit is basically, as I told you, among the open bins, we choose the one not with the least remaining space, but with the most remaining space. So from here it is, what is it? From from a pseudocode perspective, the only things that change is this guy. We are looking for the maximum instead of the minimum. So we are looking for the bin with the largest residual capacity, not with the smallest residual capacity. Everything else stays the same. So let's look at the trace table. For the first item, we open the first bin and the residual capacity is 2. Now we check at item 5 with a weight equal to 4. It doesn't fit bin 1, so we need to open a new bin, which is bin 2, and the residual capacity is 6. So we have two open bins, 1 and 2, with residual capacity 2 and 6. Now we are looking at a third item, which is item 3, weight equal to 7. It will not fit any of these open bins, no fit, no fit. So we need to open a new bin, bin number 3 with residual capacity 3. So we have now these three open bins. Let's see at item number, at the fourth item, which is item 6 with weight equal to 2. Now this is where the difference comes. So 2, before with the best fit, we located the item in bin 1. Now we locate the item in bin 2 because we are looking at the bins with the largest residual capacity. And so we will do this and we'll put the item in t equal to 2. And so now we have a different allocation than before. Now we have again still 3 bins, but with 3 bins, and the residual capacity are 4, 3, and 2. Next item. Item is the fifth item, item 4 with weight 6. It doesn't fit in, it doesn't fit in any of the bins. I need to open a new bin. Bin 4 with residual capacity 4 now. Let's look at the last item. The last item doesn't fit anywhere, so we need to open a new bin, and this wasn't a great choice. So we use 5 bins when we have the worst fit. So we have seen 4 packing rules, and each of these packing rules, when used inside the random algorithm, will generate a different random algorithm for a given bin packing problem. Each of these 4 packing rules, as we already saw, have as an input, takes as possible input the permutation. So now what we really need to do in order to finish the step, generate a random solution, is to look at how we can generate a random permutation of a given list of items. Okay, so the generation of a permutation is random. So there must be, we want to generate a random permutation, so which is a different order of the element in the set. So the idea is very simple. We have an array, with a list of elements in a certain order. We generate 2 random numbers, and we decide to swap the position of those items in those positions. So this is the very simple pseudocode. We have an array 1n, which again is consider these are the position, and inside this there are the value of the ID of the item. And then the output of this is a permutation of the element in A. How do we do that? With a for loop which scans the item and randomly generate an index and switch the 2 items in position I and in position J. It's better if I show you how this happens on the trace table. So the only thing that you need to remember is that the for loop is a descending for loop. So it's a decreasing for loop. It starts from the last item and goes down to 2. So let's see how it works. So we have these items. The items are put in this order: 1, 2, 3, 4, 5, and 6. In position 1, there is item 1. In position 2, there is item 2. In position 3, there is item 3. In position 4, there is item 4. And in position 5 and 6, there is item 5 and 6. So the for loop starts with I equal to n, which in this case is equal to 6. And the random step of this procedure is the generation of the index j. The random generation is the following: choose a random index, so generate an integer between 1 and between 1 and the current value of I. So what does it mean over here? If I is equal to 6, I generate a random integer between 1 and 6. So in this case, I generate 3. So what does it mean? That I look at this array, I look at the item in position 3 and in position 6, and I swap them to obtain this other item. So the item in position 6, which is 6, goes in position 3, and the item in position 3 goes in position 6. And this is the new array. But I'm not done. I continue. So I now is decreased and goes to 5. I generate a number between 1 and 5. I generate a number 1. This is absolutely random. That means that I need to look at this array now, look at the items in this array in position 5 and in position 1, which is this guy, and I swap them to obtain this other guy. So look at this. So we have changed the position. This is an iterative swapping. So we have the previous swapping, we swap this, and now the other swapping, swap this and this. And we go down. I is equal to 4. I generate a number between 1 and 4. I generated the same value, so j is equal to 4. What does it mean? That I do not make any swap, and so the array stays the same. And this is again also part of the randomness of this algorithm. I may start with an array and end up with the same array just because I always generate a specific number. But this is the randomness of this procedure. So then I goes down to 3. J is a number that has to be generated randomly between 1 and 3. So it could be only 1, 2, or 3. I have 2. I swap the item in position 3, which is this guy, with the item in position 2. So I swap them. 2 goes here and 6 goes here. And finally, I is equal to 2. I can either swap I I can either generate j between 1 and 2. So I generated 1. So I swap these two items, the one item in position 1 with the item in position 2. And then this is the new random permutation. So from this, I generated this random permutation. Of course, this is random because the value of j, this is random. Is this the only way of generating a random permutation? Absolutely not. You can do in different ways. This is just one way. Let's put everything together now. So this is actually, this is the random search algorithm for a bin packing problem or a bin packing based problem. So we have, again, remember now we are at the random search algorithm. So basically it's generating a lot of random solution and taking the best among the random solution. So we have a max trial, which is again the number of random solutions that we are generating. And so we initialize our two variables, which keep track of the best solution. So we have one for loop, which examines only the generated solution. These two guys, these two lines here, these two guys together generate a random feasible solution. So differently from the random algorithm that we had for the knapsack problem, For the knapsack problem, what we were doing is generate a possible solution and check its feasibility. Here, the way we are generating a solution for the bin packing, we are making sure all those packing rules that we have seen, these packing rules generate already a feasible solution, which is random. So the packing rule ensures feasibility, so we don't need to check feasibility because it's embedded in the packing rule. So once we have generated a feasible solution, we compute its objective function, which is actually the number of being used, and we keep track of the best among all the feasible solutions that we are generating. And this is the random search algorithm for the bin packing problem or for bin packing based problem, which are those problems for which we have a solution which can be represented with an integer vector, and for which we have the basic decision to assign element of one set to element of another set. On Tuesday, you will see how to actually implement these algorithms for specific problem and for specific instances. I will also add additional practice exercise to practice on the design and implementation of random search algorithm for this class of problems. Thank you, and I'll see you on Tuesday, and stay warm.